Hello, Podsters. Welcome to a brand new show, Pod Chat. Today, in our very first episode, we'll wander in the realm of physical sciences. Listen Neel and Shivam chat about pulsar timing arrays and detecting gravitational waves. Let's dive into their conversation.
Hi, thank you for having me. Can you introduce yourself to our listeners?
Sure, I am Neel Kolhe. I very recently graduated with a master's in physics with a specialization in astrophysics from St. Xavier's College, Mumbai. I am currently working a research group called the Indian Pulsar Timing Array.
So, you were born and brought up in Mumbai, right?
No, I was not.
Oh.
I was born in Pune.
Okay.
I lived there till I was 10. I had my education till 4th standard there. And because of better job prospects, my parents moved to Mumbai and I've been here since I was 10.
So, you are here since you were 10?
Yeah.
And how were you as a child? Were you always fascinated by science?
I was always very curious about random things, not particularly about physics or astrophysics or anything of the sort. I always wanted to be a new kind of scientist every single day. I had a lot of encyclopedias growing up. I read them a lot. And one day I wanted to be a chemist because, oh look, shampoo or pani mix kiya, oh jhaag banta hai, nice, chemicals, fun. And the next day, I maybe read an article about clouds or something, and oh look, the cumulonimbus clouds look really pretty. So today I want to be a meteorologist. So, yeah, the kind of the physicist thing kind of stuck rather late.
Okay.
I wanted to be a different kind of scientists every couple of months till it landed up to be physics and just stuck, I guess.
So, but you were sure about that you want to become a scientist?
No, not really, no.
No?
I was just into science. I would have been perfectly happy doing any job which let me explore things around science.
And any curious job?
Yeah. I don't think such an academic bite ke research karo wala job was I don't think so. I understood what that is till very late in life. What exactly does a professional scientist do?
So, it was just basically your curiosity?
Yes.
Of trying to find out stuff?
Yeah. Very random stuff. I was an extremely random child who got weird fixations and fixated on certain ideas for days and days.
I can completely feel that. I think every science starts with that. As a really curious person, and then slowly figuring out what they really want to do in life. How were you in school?
A very mixed bag. I guess every single time my school had a parents-teacher meeting, the teachers always used to say to my parents, he can do a lot better. We don't understand why he isn't.
Oh,
and that has always been my life till a couple of months ago. The teachers have not stopped saying that. I still don't know what this better is yet, but I guess I'm trying.
Was it more like when people say कि दिमाग तो बहुत है, बस पढ़ाई नहीं करता है?
Yeah, I guess, yeah. That has definitely been a thing. Yes.
And what was the reaction of your family when you told them that yes, I want to do science?
So my family is generally supportive of whatever I do. Both of them have science degrees. They never used them though. So my mother has a master's degree in chemistry, and she wanted to do research actually, but she never could because of certain reasons. And my dad has a BSc in electronics.
Okay, so both of them are from scientific
backgrounds. Yeah. Both of them have degrees in science, but they never use them in their career as much. My mother was a teacher for many years, a junior college teacher. But my dad never used his science degree ever. And both of them moved to media or arts related jobs. And they basically these days never ever use any of the knowledge which they have learned in their degrees. Okay. I guess their degrees did instill in them a kind of general scientific temper. So they are not orthodox in any particular way.
Okay.
So the education definitely helped them, but they do not use their degrees in their own jobs these days. And they kind of had similar expectations कि हाँ ठीक है बच्चा science का degrees कर रहा है, but his talents seem to be more oriented towards literature or something creative. So they always wanted me to take up a course or a degree which is more oriented towards something more humanities related,
arts.
Yeah.
Okay, so they always saw you as a curious kid, and they thought that your curiosity would suited to something like literature and arts.
Yes. Yeah.
And do you feel the same? If you want a scientist, if you want a physicist, because you spent more than 7 years, beginning from taking science after 10th, and now you're completed masters in astrophysics.
Yeah.
If not physics, do you really think you do good as a literature person?
Yes, yes, as in I would have enjoyed doing it. Not as in I don't know if I would have been a good person who's like into literature and stuff. I don't know what you call it, literary artist, a writer or something. Because I never got a proper opportunity to try that out, and I did want to. So every step of the way, somewhere in the back of my mind, I've always had this thought of, okay, a huge chunk of my inspiration to get into science in the first place was through science fiction. And I always wanted the time and the mental headspace to get into science fiction, write some of my own stuff. In BSc, jab thoda time rehta tha, I used to participate in competitions and do fairly well in those competitions as well. Writing competitions, science fiction writing competitions. But बाद में जब, especially towards the end of BSc and बीच का जब masters का चीजें start हुआ, no time at all. You barely get time to breathe. It's very unfortunate. In the future though, I do want to pursue more writing. I do want to
more writing as in more science communication.
Science communication as well as fiction writing. It has been something which has been very, very close to my heart. And I have not been able to find time for myself.
And I feel like as a science person who has completed your masters in physics, you have more knowledge into the actual science. So I feel like you'll be able to make science fiction more believable.
Let's see how that goes. Every single person who wants to write feels that they'll end up being a very, very good writer. Most times the writing is pretty shit when it starts off. It takes a lot of practice to write a fairly decent
because
piece.
When you already know the science facts, when someone will say सच के आसपास का झूठ ज़्यादा believable होता है.
Let's put that to test. I am skeptical about myself right now, so let's see. I'm very happy that you have such great faith in me. I don't have so much faith in myself. So. Let's see.
The next part, let's go to the actual science part.
Sure.
So now you have completed your masters in astrophysics, and to complete that, you had to do a 5-month research, and your research topic was detecting gravitational waves using pulsar timing arrays.
Yep.
So what is it? How does it work?
So let's just start with something very, very basic.
Okay.
So what are gravitational waves? So everything which has mass attracts everything else which also has mass. Newton's universal law of gravitation. Einstein's insight into this was very simply put that the communication between these two masses is not instantaneous. So for example, if I have two balls in my hand, one in my right hand, one in my left hand, and they're clearly mutually attracting each other with some very tiny amount of force. If I move the ball in my left hand, say move it away from the right hand wala ball, the information that the ball has moved and now the gravitational attraction has weakened takes some time to be communicated between those two balls.
Yes.
And that information is communicated at the speed of light. That is basically Einstein's insight into gravity, put in a very, very simple way. And this delay in the way the information reaches from one object to the other can basically be summarized in equation as a wave. The wave, which can carry energy, in this particular case, is called a gravitational wave. An analogy to this in electrodynamics is a moving charge. If we have a moving charge which has a field, and if we move an electric charge, say we accelerate the electric charge, it radiates light. So in a similar way, in gravitation, the charge equivalent is mass, and if we ever accelerate a massive object, it emits gravitational waves. The analogy is the same. Accelerating charge emits electromagnetic waves, and accelerating mass emits gravitational waves.
So the mass needs to be accelerated.
Yes.
Okay.
In some way, it has to change its direction, or it has to change its velocity, or both. So now it begs the question ki why do we feel these gravitational waves or not? हमें light तो दिखता है भाई, पर gravitational waves दिखते हैं क्यों नहीं दिखते हैं? So everything which has mass emits gravitational waves when they're accelerated, but the amplitude is very, very, very small. It's extremely tiny.
Okay.
So when I move these tiny balls, the gravitational waves which are emanated from these balls, उनका amplitude इतना कम होगा that you won't even feel them. It will take an extraordinarily sensitive detector to ever detect these. So to detect gravitational waves, you need things which are extremely massive. And some of the most massive things in the universe are black holes. And that is why the Laser Interferometer Gravitational Wave Observatory, Ligo, was able to detect gravitational waves from colliding black holes in 2015 was the first detection, I think. When something as big as a black hole somewhere off in some other galaxy basically interacts with another black hole, this particular interaction, the change in the mass ratio, not in the mass of the object. It's basically both of them are the pair of the black holes are basically not in a place where their distribution of masses is not symmetric. So it's not a sphere, you see.
Okay.
When the two masses, one of them might be larger, one of them might be smaller, kind of generate like a mass asymmetry in space-time, which lets them accelerate. Because, one is attracting the other and one kind of chasing the other kind of object. We won't get into like the celestial mechanics here. I'm just trying to keep it very, very simple. But it's attracting each other and kind of chasing each other in their own orbit. And this mass asymmetry and the chase due to that generates gravitational waves. You don't need asymmetric masses. Symmetric masses can also
create
gravitational waves.
And these gravitational waves are detected. Right now, the only tool that we have to detect these gravitational waves is LIGO.
And LIGO can detect gravitational waves from stellar mass black holes. What this means is black holes which might be of one solar mass to about, say, a few hundred solar masses. Few hundred is also like the upper limit. It's usually about 150 they expect to detect gravitational waves from 1 to 2 solar masses. Usually it's stuff from 3 solar masses to, say, I think the most heaviest till date is like 87 among the pair.
So even for LIGO right now, you need to have a really massive object creating that gravitational wave for it to be detected.
Yes.
And I think LIGO itself is a really sensitive...
It is very sensitive.
Can you give a brief about what LIGO is and how it works?
Sure. Definitely something which I have read about before, and I kind of also volunteered with LIGO for this and science communication stuff some time ago. So I can tell you a bit about LIGO. So the way LIGO works is, imagine two arm lengths which are perpendicular to each other at, say, 90 degrees. At end of each arm, they have two mirrors, and where the arms intersect, they have two lasers which are fired perpendicular along those little arms, and these lasers bounce off mirrors and come back at a particular point. And these lasers are kept thoda sa out of phase. They just don't align really well. One beam kind of arrives thoda sa late, and one beam arrives, say, at a calibrated time.
Okay.
And the expectation is, if a gravitational wave passes by, a gravitational wave is stretching and squeezing of space. So literal space and time stretch and squeeze as a gravitational wave passes by. The expectation is, as it passes by these arms which are perpendicular to each other, these arms will be stretched and squeezed, and the length of the laser beam then is kind of reduced. The beam has to travel less. So the beam which is coming back at the point where these two beams meet comes back later or earlier, and this difference in the phase can be picked up by a detector, and this difference in phase then will kind of look like a waveform, or it might look like it might have a particular structure which you might expect from a particular kind of interaction. And then
looking at that structure, we can then figure out
what kind of interaction it was. They use very advanced algorithms, cross-matching algorithms to figure out what kind of wave it was, what kind of binary it was. It also tells you some information about their mass, tells you the information about how far away the black holes were, how far away they were.
From which direction the gravitational
general direction, yes,
came to us.
So currently there are two LIGO detectors, and there's one called Virgo in Europe. And these three detectors can kind of pinpoint in general in which area of the sky the gravitational wave is coming from. It's not very accurate, but you can generalize the general location to I don't know how many arc minutes, but they can localize it to a fairly accurate spot in the sky. So what we expect is, if a black hole if there's a black hole neutron star merger, as the neutron star approaches the black hole, we expect that the tidal forces will be so strong, the same way, say, the moon and the sun kind of pull the Earth's water thoda sa upar niche due to their gravitational interactions, and we get tides. Similarly, when the neutron star comes very, very close to the black hole, the tidal forces will be so strong that the neutron star will essentially be ripped apart as it is consumed by the black hole, and they become like a larger black hole together. During this ripping apart process, we expect some high energy signatures to be found via EM, electromagnetic waves, along with the gravitational waves. And these will be in the X-rays and gamma rays for the most part. You might even later get a radio afterglow in the radio energy range. So we do expect that to happen with a black hole neutron star interaction. We still haven't seen one. I might be wrong. We have bada sa asterisk यहाँ पे. Bada sa asterisk on the whole thing, by the way, because I'm not an expert in LIGO. We are talking about LIGO because it's really cool.
Because LIGO is right now one of the tools that helps us detect gravitational waves. Exactly. But what you have worked on, the pulsar timing arrays, it can also be another reliable tool to detect the gravitational waves.
Yes. So let's talk about frequencies for a bit. Frequency as a concept. So Shivam, here's a question for you, because I've talked a lot now.
Okay.
So how do you define frequency?
When I think of frequency, I think of rotational.
Okay.
If you have a moving object, a circularly moving object, the amount of time it moves in a fixed frame of time is a frequency. So in case of this, we can say frequency as the rate at which an event occurs in a fixed frame of time is frequency.
Yeah. So if something is occurring a lot in say 1 second, if something happens say 100 times a second, you might get it 100 hertz ka frequency hai uska. If it is happening 1,000 times a second, we might say it has 1,000 hertz ka frequency. So the Ligo ka frequency range of the gravitational wave oscillation is in the hearing range of humans for the most part.
Okay.
So it is from a few hundred to a few thousand. I might be wrong again, but asterisk yahan pe, it's definitely in the few hundreds if I'm not wrong.
Okay.
And Ligo can only detect that much. But there are other objects in the universe which might emit gravitational waves which are at frequencies which are much higher than that. And LIGO won't be able to detect that because LIGO's arm length and the technology basically makes it sensitive only to that particular range of light.
It can detect.
Exactly. The same way our human eyes can detect only the visible part of the spectrum for the most part, and say bees perhaps can detect some ultraviolet part of the spectrum, and radio telescopes, for example, can detect the radio part of the spectrum. LIGO can only see the few hundred hertz part of the spectrum. Please correct me in the aftermath if it's not just few hundred and thoda zyada hoga to. I might be wrong.
Okay.
So, if there are black holes which are bigger than these few tens of solar masses or a few hundreds of solar masses, basically LIGO won't be able to detect them.
The gravitational waves will be just too strong for LIGO.
No, the wavelengths will be much larger. They won't be strong per se. The amplitude, the wavelength will just be larger than what the particular detector can detect. So there are two experiments which are currently being developed to detect gravitational waves which are of longer wavelengths than what LIGO can detect. One of them is called LISA. It's quite like LIGO. It's an interferometer basically which is going to be in space. 3 satellites which are going to basically follow Earth. Each of them is also going to have a laser firing a laser at the other satellite, and satellite's arm and the distance between the two satellites basically will reduce and increase as the gravitational wave passes by. It will be detected.
So it's like the actual structure of LIGO, but in space.
There are actually 3 satellites, so there are going to be 3 different beams of light being exchanged. So it's way more complex than LIGO. It's way more sensitive as well. So it is expected to pick up gravitational waves from objects which are in 10⁶ solar mass range, which are expected to be like black holes at the center of smallish and close by galaxies. When galaxies merge, galaxies are expected to have like black holes in the center of them. Yeah. So when these galaxies merge, it is expected that these black holes also merge, but we do not know how these black holes are brought together. So it's a big mystery. It's called the final parsec problem in astrophysics.
Final parsec problem.
Yeah.
Wow.
So the problem is such that, okay, sure, gravitational waves can decay orbits, but to make gravitational waves decay orbits, the black holes have to be really, really close to each other. So, for example, if you have 2 black holes, one in its own galactic center, and if these 2 galaxies are very, very far away and they are on a merger or apart, let's say, the orbital decay between these 2 galaxies is not caused because of gravitational waves till they get really, really close to each other. वो होगा थोड़ा सा, but वो orbit decay इतना छोटा होगा it will take more than the age of the universe for these 2 black holes to merge.
Okay.
Till they are brought really close to each other, उसके बाद gravitational wave it takes priority in the way the gravitational wave emission decays the orbit faster than anything else can.
So the gravitational waves emission will accelerate the decay of the orbit
when they get really, really close to each other. So the question is, what then brings these 2 black holes together? So if the orbits have to decay, there has to be maybe some kind of friction, dynamical friction, which might be brought about by stars in the galaxy interacting with each other. There might be tidal forces in the circumbinary disk between the supermassive black holes. There could be many, many things which could cause the orbit to decay to a distance of these 2 black holes, where actually gravitational waves could take precedent and actually make the final step of merger, which might happen. And we have some answers to what might cause this orbital decay to the black holes, to bring these 2 black holes from 2 different galaxies really close to each other. But we do not have a definitive answer कि process क्या है, step by step. ये पहले होता है, ये बाद में होता है, ये बाद में होता है. We do not know the exact process of what brings these 2 black holes close together. And why is it called the final parsec? Because at a distance of about a parsec to a few parsecs, depending on the mass of the black hole, the gravitational wave interaction kicks. So the final parsec problem is what brings these 2 black holes together till the distance of the final parsec. So this is called a final parsec problem. And LISA, are perhaps going to help us answer these particular questions about what are the rates of mergers of supermassive black holes. So, kind of an interesting thing.
That is actually really interesting.
It is.
So, you have to figure out what is causing it. As you said, it can be some kind of friction from stars.
Dynamical friction, yes.
Dynamical friction. What is dynamical?
Okay, I am not an expert in orbital mechanics of galaxies, but it is basically, a galaxy has millions of stars.
Yes.
And these orbits interact with, the orbit of one star interacts with the orbit of the other star.
Yes.
I might be completely wrong here. Again, big asterisks
Yes.
here.
Yes.
I learned this in the galactic dynamics course, but
yes.
we have forgotten about it clearly. After an year
6
of
months
taking the course, completely forgot about what it exactly was. So let's just keep it at the gravitational interaction between multiple stars together can be such that orbits can decay, I guess. We'll just keep it at that. It might act like
those stars interact. So we have two black holes in the center of galaxies.
Yeah.
And when they are coming close to each other, the orbits of stars around each of them will cause some kind of a
perturbation,
which will help them come close to each other to that final
but dynamical friction is not just for these black holes. Dynamical friction is a thing which happens in galaxies in general.
Okay.
So even if you don't have black holes in the center, other parts of the galaxy will be affected by these stars' interactions. So dynamical friction can be it's like a general phenomenon which happens in galactic dynamics for certain.
So coming back to pulsar timing arrays.
Yeah, finally. So what are pulsar timing arrays? So these were massive black holes, 10⁶ solar masses.
Yes.
We expect that ancient, very old galaxies and very old supermassive black holes to be of mass ranges 10⁸ to 10⁹. So these supermassive black holes, as we call them, are between 10⁶ to 10⁹, and the more massive range lies between I guess 10⁸ to 10⁹, to maybe even 10. Some speculation goes to 10 as well. Solar masses, gigantic black holes which we expect to see in very high rates of galaxies, as in galaxies which are very, very far away from each other. Maybe some of the first ever galaxies found in our universe might have been these galaxies which might host these very, very large supermassive black holes. And these black holes, when they interact with each other, we expect the frequency of these gravitational waves to be in the nanohertz region. Nanohertz being 10⁻⁹ hertz.
That's very small.
Very, very tiny, huge wavelengths spanning many, many, many light years. Gigantic gravitational waves. So to detect them, you basically need a system which is also as big as a galaxy. But how? Well, okay, LISA you can build to detect things which are on massive black holes. How will you get a detector which is basically as large on the scales comparable to a galaxy?
Yeah, because if the wavelength itself is
light years
exactly
wide,
we may be in a gravitational wave right now and we
won't be able to detect it exactly.
Yes.
So let's keep the problem there. Okay, let's put a pin in this problem and get to thoda sa tangent, and we'll merge both of these points together to come to our really creative solution, which was actually thought about back in the 70s by some scientists. So we talked about neutron stars, which are these dead cores of giant stars, which have basically burnt out all of the fuel and are degenerate stars. They're very, very compact, very, very massive. So imagine a stars or a couple of stars worth of mass compressed in a diameter which is 10 to 17 kilometers. Fun fact: Thor's hammer is supposed to be made from matter from a neutron star.
Yes,
it's supposed to be. That's why it's supposed to be that heavy.
Yes.
So some of these neutron stars, especially neutron stars which are not accreting, all neutron stars basically, because of the law of conservation of charge, all the charge from the stellar mass worths of mass has to still be preserved in that little tiny area. Basically, neutron stars, because of the law of conservation of charge, have a whole bunch of charge packed in a very, very small area. That means it has very, 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 very strong magnetic fields in a very, very small area. So neutron stars are some of the most strongest magnets out there in the universe. And various radiative processes in these magnetospheres and from inside of the star and the magnetospheres of the neutron star basically lets it be very, very bright in the radio region along its poles, all along its magnetic poles. So in neutron stars, the same way as the Earth has, the magnetic poles and the rotational axis of rotation don't line up.
Okay.
So the star, as Earth does, rotates on one axis, and its magnetic poles, which are not aligned, rotate on
some other axis.
On a different axis. So when a neutron star rotates around its axis, its two poles, which are like very, very bright in radio light, basically act like a sweeping lighthouse, which is like moving around, which kind of rotates around space. And if you are in the line of sight of one of these beams, it will basically look like a blip or a pulse coming towards you. And such neutron stars, which we see as these pulsating objects, radio light, are what we call it as pulsars. The discovery of pulsars is its own story, in which the PhD student Jocelyn Bell was not given the Nobel Prize, while the PhD supervisor was. And it's its own very, very interesting story, and you should look up what exactly happened then. Pulsars were discovered, I guess, more than about 50 years ago now. And because they are neutron stars which can be so regularly be observed with radio telescopes, have led to like a whole bunch of different discoveries in astrophysics. So even before pulsars were used as pulsar timing arrays, they were used to detect gravitational waves, but not gravitational waves in the 10⁻⁹ Hertz solar region, but gravitational waves from two neutron stars decaying in their orbit. So the first indirect detection of gravitational waves, even before Ligo was a direct detection, was a pulsar binary called the Hulson-Taylor pulsar. In the 70s, a pulsar binary was discovered. So two pulsars rotating have an orbit around each other in a binary. And these two physicists, Hulson-Taylor, they made continuous radio observations of these two pulsars. They kind of basically observed the pulsar for a very, very long time, and they kind of figured out how the pulsar orbit is decaying. And the orbit decay, the pulsars were basically every single rotation, uska orbit thoda sa chota ho raha tha as they went around each other. They basically corresponded this decay in its orbit equivalent to the amount of gravitational wave emission because they were not detecting gravitational waves, right? So what they calculated was, if the Hulson-Taylor binary pulsar is emitting gravitational waves, uska orbit kitna decay hona chahiye. They kind of calculated that, and then they measured the Hulson-Taylor binary pulsar, and they saw that, oh wait, the binary pulsar is decaying in the exact same manner. The orbit is decaying literally, it was not linear, but point to point in the same way what they predicted. So that was the Hulson-Taylor binary pulsar. So pulsars have like a rich history in gravitational wave physics in the first place. They have been used for stuff like this, but our particular use for pulsars is using pulsars as very, very accurate clocks. So because pulsars rotate around their axis, and they are very, very bright in radio light, and you can detect these pulses. These pulses are extremely periodic. You can predict when the next pulse is going to be if you have like a set of pulses recorded before. And because you can you can expect when the next pulse is coming, you can essentially use pulsars as very, very accurate clocks. Well, there are a special kind of a pulsar called millisecond pulsars, as the name suggests. The rotational frequency is like, they rotate, one rotation is finished in about a millisecond. So these millisecond pulsars are exceptionally stable, as in the rotational frequency absolutely does not change, more so than other pulsars do. They also show very low glitchy behavior. So what are these glitches? Glitches are like internal changes in a pulsar which might cause the rotational frequency of the pulsar to change. So millisecond pulsars show very little of these glitches. So we can essentially use millisecond pulsars as very, very, very accurate clocks. Because they are very, very accurate clocks, we can use them to detect gravitational waves. Because gravitational waves are the stretching and squeezing of space and time, if a gravitational wave is passing by a millisecond pulsar, its pulse time of arrival to a telescope will either be delayed or it might reach us faster. And this change in the time of arrival of these pulses can be characterized as a gravitational wave being detected. And that is what we expect to do with pulsar timing arrays. So what exactly are pulsar timing arrays? Our radio telescopes here on Earth, for example, our group, the Indian Pulsar Timing Array, which is operated from the National Center for Radio Astrophysics in Pune, uses the Giant Meter Wave Radio Telescope, which is an excellent, very, very sensitive telescope here in India, to keep track of a set of pulsars spread all across the galaxy. And every observing cycle for, say, about 20 to 30 days or maybe more every single year, we keep track of these pulsars. We observe these pulsars on those nights of observation, and we basically time them and see what the rotational frequency is, how the pulses are coming, the time of arrival, so on and so forth, kind of record this data. And because these gravitational waves have a light years scale, it could detect one, I guess, a wavelength of it might take months. So, you can have a cadence which is between days and months to detect the entire wave, gravitational wave, if we ever detect one. We haven't detected gravitational waves yet. It's an expectation that we might detect these gravitational waves very, very soon using these pulsar timing arrays. So, what do we expect to detect in the coming future, and some other groups like Nanograv, which is like the PTA for North America, and have already claimed that they might be starting to detect gravitational waves. थोड़ा सा किधर तो signal मिल रहा है. They call it a red noise process in their datasets. What they expect to detect at this moment, at least, is not gravitational waves from individual binaries, but something called as the gravitational wave background. So, because there are like many. I don't even know the exact number. There might be many of these black hole binaries all over the universe emitting these gravitational waves. These gravitational waves are reaching us in an incoherent and uncorrelated background. So, all of these gravitational waves overlapping on top of each other, which will kind of make like a noise flow, like a baseline gravitational wave background, which could be detected everywhere. The same way we have the cosmic microwave background, we also have the gravitational wave background for all.
It's like a swimming pool full of people.
A swimming pool full of people making all these ripples on a pool. Yeah.
On the pool. So all these ripples are all different gravitational waves, but because they are all interacting with each other, we just see noise.
Exactly. But you still can have an amplitude which could be detected. You still have a general amplitude. So what we expect to detect in the near future is this gravitational wave background. And as our experiments become more and more sensitive, especially towards the end of this decade, we expect the square kilometer array to come online. And the square kilometer array is going to be a radio telescope with basically a surface collecting area of about a square kilometer, going to be very sensitive, is going to join the pulsar timing array effort. India is a part of the square kilometer experiment. We are funding it partially, along with many other countries. We expect to not only detect the background and characterize the background really well, but also to detect individual binaries of supermassive black holes going around each other and on a merger orbit.
Once you subtract the noise.
Once you subtract the noise, once you make these experiments very sensitive. So, in these single binaries, in these individual binaries, which we expect to detect like a decade later, you have all kinds of orbits. You have orbits which are circular, just like perfectly circular orbits going, like two giant supermassive black holes just going around like a circle and decaying slowly. You might have eccentric orbit, like elliptical eccentric orbits in which eccentricity is very high, and there's like a beautiful elliptical loop which one smaller black hole is kind of making around a larger black hole to keep the larger black hole at focus. You can have parabolic orbits, where you like have a slingshot which is unbound, and you have hyperbolic orbits, which is basically an unbound orbit in which the pair regains more energy as it leaves. So, till date, for supermassive black holes, for these binaries to be detected, we need to figure out how these signals will look like in the pulsar timing array dataset. So, the pulsar timing array datasets, as I basically said, are these graphs in which we basically have kept time कि ये pulse कब आ रहा है हमारे पास from these various pulsars. And if a gravitational wave is passing by, there will be a characteristic change in the way these pulses arrive, and we'll be able to tell कि what kind of a binary it is. So, the characteristic change in the shape of the time of arrival curve, which we'll eventually have, will correspond to different kind of orbits. So, till date, we have a good characterization of how circular orbits will look like in the PTA dataset, of how eccentric orbits will look like when observed by PTAs, of how parabolic orbits will look like when detected by PTAs. But till date, we do not have a prescription, or we did not have a prescription of how hyperbolic orbits emit gravitational waves, and how these gravitational waves from hyperbolic orbits interacting with pulsars will look like in the pulsar timing array dataset. Enter the problem given to be my guide, Professor Achamvitu Gupta from Tata Institute of Fundamental Research. He suggested that I, with the help of our collaborators, work on this particular problem for my master's thesis.
Figuring out how gravitational waves are produced by hyperbolic orbits.
Not how they're produced, we know how they're produced.
Okay.
Of how these gravitational waves produced from hyperbolic orbits interact with pulsars, and how they will look in the pulsar timing array dataset.
So give you a signature.
Yeah.
Basically.
Yeah.
So, okay. So if you see this pattern in the change in the pulsar timing,
yes,
that means that it's coming from a hyperbolic
orbit. Precisely. So that is kind of what I worked on.
Okay.
I had to first understand how hyperbolic orbits work in the relativistic sense, because these are not Newtonian objects. These are objects moving very rapidly. They are black holes. The orbit has to be relativistically accurate. So I had to use something called as the post-Newtonian approximation of general relativity, which is a way to solve dynamical problems in GR. GR is a notoriously non-linear theory, and it's it's very hard to solve basically the two-body problem of moving objects in GR. So you have to use, there are a lot of methods people use, but we used something called as the post-Newtonian approximation. It's a tried and tested method. The first expectation of the precession of Mercury, done by Einstein, was used by something akin to the post-Newtonian approximation as well. So we basically used the post-Newtonian approximation. I kind of tried to develop a prescription in which I tried to figure out how the hyperbolic orbits evolve relativistically using the the post-Newtonian method. Then calculated how the gravitational wave from this post-Newtonian hyperbolic orbit will look like. This work was already done by my guide. I just reproduced that work for my own understanding. And once this was done, the novel effort in the entire project was how these gravitational waves interact with pulsars and what the signature is going to be. So in that particular calculation, I had to input equations of where the position of the pulsar, where the pulsar is going to be in the sky, the positions of where the gravitational wave source is going to be, and then finally how the gravitational wave interacts with the pulsar. So when you kind of put all these equations together in a particular order, I kind of developed a prescription, like an algorithm of how to go ahead and end up with something what we called as pulsar timing array residuals, which is the signature which we expect to be detected in the gravitational wave. So this work was largely based on one of my colleagues' work, Abhimanyu Susabanan, who worked on this exact same problem but for highly eccentric orbits, a closed bound orbit. So he had already done this work, so I basically did this in his footsteps and I came up with a prescription. The prescription had some errors, as we recently found out, even after my thesis was finished.
Very recently. You're still continuing your work.
Yeah, my work still continues. The prescription had some issues. Even after my thesis was published, we did not catch those issues in my thesis, but later on we did. We are still working on that. We are still working on making that prescription more and more accurate. The project is now taken up by a different colleague of mine, Subhajit Dandapat and Prerna Rana, and I. All three of us are currently working on tackling this particular problem and making this prescription more accurate, improving the way we integrate, improving the way we basically present. And there were some bugs. We are kind of cleaning off those bugs. And once all of this is done, we'll be able to publish this as a paper, hopefully sometime early in 2022.
Oh, wow.
So, yeah, that is what my thesis was.
So, you're still on it?
I'm still working on it. I'm still working on it, yeah.
And how long has it been? The 4-month project has now extended to almost a year?
Almost a year, yeah.
Yes.
It's almost been like exactly a year. It will be exactly a year next month since I started working on project, yeah.
So, apart from the entire pulsar timing arrays, I think I have a few questions.
Sure.
What is your long-term vision? What do you want to achieve? Like, your main vision right now is to complete your paper, which will be published in the next year.
Yeah.
And then what?
So me personally, in the near short term, I'm looking for PhD positions in many different kinds of astrophysical areas, and not just in gravitational waves or pulsar timing. I have worked on other things in the past, in radio astronomy, and also in like simulations. I love hydrodynamical fluid simulations of objects and all it is. I love doing that. So anything of that sort, I'm looking for PhD positions in all of these various fields. It'll be nice if I am able to become like a full-time academic. Very hard to do, but who knows? I'm going to take that shot. On the side of, regardless of what happens, I want to be involved in science communication more and more. Outreach activities are something which is very close to my heart. I strongly believe that scientists should be involved in outreach and communicating things they do to their own communities in like an accessible way, so that people understand where their tax dollars are going to.
Yes.
And also in general to make people curious about the world around them, because in the end, when all the material needs are met, curiosity is like, if I may use the word very, very cautiously, curiosity can be a very spiritual experience in a way.
Oh yes.
In which, especially like it satisfies you. It kind of makes you feel that the time you're spending is kind of worth it.
So, as you said that scientists should be more involved in science communication, and you also want to be a part of academia.
Hopefully.
What are the things, according to you, in academia that require improvement?
I'll focus this on Indian academia. I am closely associated with it, and eventually might end up in it. The biggest thing which I have noticed, apart from the lack of funding, apart from weird corruption, apart from the very little number of scholarships which are available, it is the way in which scientists are chosen for various positions which are out there. The methods in our country, due to the function of the number of institutes we have and the function of people who want to get into this, end up becoming very dull and very repetitive, being entrance exams. at every single
Yeah,
level
that's
of
true.
academia. Every single level of academia.
You have exams for everything.
You have
to give entrance exams.
Yes.
There are criteria, and also
Yes.
because there is such a big difference in the number of people who actually attempt the exam and the seats which are available.
Yes, exactly.
There are like 6 lakh, 7 lakh people who give the exam, and
Exactly.
we have how many seats?
Hundreds.
Some 100. We have 100 seats
Yes.
out of the 6 lakh people that give the exam. Wow.
So because of this, I'm not saying this is a bad system or the system is problematic. The thing is, you are selecting for a very particular kind of science.
Yeah.
Which is not a bad thing.
A
Which is not a bad thing. It is completely understandable to have, for a scientist to have those particular kind of analytic skills in which they are able to solve problems in a given amount of time, so on. But that is not research, as you just very pointedly noticed that I have been working on this little tiny project for over a year. So the scales at which problems are solved in research, they are not on the time scale of couple of minutes ka MCQ solve. It requires different kind of skills which are not at all cultivated in our students, and even if they are, those students might not get a good opportunity to be selected for all these research programs which are out there, PhD programs or other research programs which are out, which is very, very sad. For all intents and purposes, India right now is selecting for a very, very monotonous kind of a scientist. I know so many people around me who are boundlessly curious and are boundlessly talented in ways other than giving entrance exams, and they are good researchers. They are amazing researchers and they have done amazing projects. But if they want to take up a PhD position in India, or even if they want to take a master's position in India, they have to crack these entrance exams, and these entrance exams cannot evaluate their projects, or they cannot evaluate their creativity, which they have spent years honing and understanding. So, that is something which we need to work on. We need to work on having alternative ways of evaluating people who have research experience and are not just good in physics. They should be good in physics. Of course they should be. There should be like a baseline which they need to understand and kind of get to the place where they are. But that baseline should be met by the BSc and the MSc exams which they are giving. So once the evaluation pattern and the way the students are evaluated at the BSc and MSc level, that should be a good enough cutoff. If and when those courses are improved, that should be like a good enough cutoff for the research institutes to understand the basic caliber of the student. After that,
this person is capable.
And after that, a whole bunch of the selection should be based on how good of a problem solving the student.
How much of a creative thinker this person is when it comes to research, problem solving. Because also the next question joins into it, because research isn't always calculations and equations and running a simulation and getting the answer. 9 out of 10 times, you won't get the answer. If you're running a simulation, you won't just run the simulation and you get, this is the answer, this is the graph, and then you publish it. You have to solve a million bugs, you have to solve a million syntax errors. And then you get the actual answer.
You have to stop yourself from being depressed that it isn't working. It's an important factor.
Yes, so research is not always as they show in the movies, but sometimes research does get really boring. As we talked about that, this one simple research of figuring out the hyperbolic orbits, it's almost going to be 1 year now.
Multiple people working on it.
And also multiple people working on it. It's going to be more than 1 year now. So there must be times during the research when things are getting really slowed down. They're getting really boring. So are there any problems that you face where the research becomes a bit too monotonous or too draggy? And what are the things that you do to keep yourself motivated, to keep yourself inspired to keep going?
Of course it happens. It has happened not just in this project and some of the previous projects I have been involved in. It happened back then as well. It especially happens because the goal is, sure, when you're doing a master's thesis, especially. Master's thesis is nothing, okay? I am a complete amateur. This is not coming from like an expert's mouth or anything. A master's thesis is nothing. It's like blip. Kuch nahi hai iska, zyada value nahi. Compared to large scheme of things, people work way harder and deal with much harder problems in their life. But again, very subjective from just my perspective. When you're dealing with a problem which is supposed to be a research problem, you know for a fact that the answer is not out. You are supposed to find the answer for yourself, which can be an exciting thing, which can be its own motivation. It can also be a very, very depressing thing if you get stuck in a particular place. And the thing is, sometimes if the research problem is in a field which you are not acquainted with. I knew about gravitational waves before I went to this particular research, but I had not sat down and worked out problems of relativity on the scale which I did here. I did not sit and code as much as the scale I did in this particular project. So these scales, these scenarios were very, very new to me. And as any person in a new scenario experiences, you kind of feel this weird feeling of maybe you are not capable of doing all of this. Imposter syndrome, jaisa ki maybe I'm not worth doing all of this. This is definitely for people who are much better at maths than me, much better at coding than me, much better at physics or science than me. And it kind of gnaws at you in your own head. And it happens to a lot of students, it happens to a lot of researchers in general, and you kind of feel like giving up. As you said, it does happen. What helps you in a situation like this, what has helped me, is the point where you started this interview is what helps me. The point where you asked me what made you happy as a child when you got into science. Like that कभी भी कुछ नया सीखने को मिलता है, तब you feel like a very you connect yourself with your own childlike self, in which you कुछ नया सीखने को मिला, you solve the smallest of the bug, you get that elative feeling कि solve हो गया, nice, fun. And science, it being such a collaborative effort, it being every single problem being you standing on the shoulders of giants, as I guess some person before Newton said, you always have a feeling of you are contributing to a legacy of peoples, of cultures which have come and gone by in the past, who have gone through a lot of cultural, societal horrors, a lot of discrimination, because scientists were discriminated against back then in all cultures, in all societies.
Scientists were more like witches and wizards.
Yeah, sure. But it doesn't happen. So, the cultural struggle in science has been a very, very long one. And at times when you are stuck, it is kind of useful to place yourself in this grand tapestry of things as a newcomer, as someone who is, in the shadow of very, very cool things very, very cool people have done in the past. And it kind of humbles you. You see, ठीक है, तू नया है, तू struggle करेगा, it's fine. But all of these people did that too. And here you are doing that too. And all of them perhaps felt the same way. And all of them perhaps were inspired by the sky above them. Maybe they stepped out and looked out at the dark sky and the beautiful stars out there and found solace that even if I don't end up making like a big contribution like Einstein did, I'm contributing to the understanding of the sky above you, which is very, very pretty. And it has its own value. You find your own meaning in that. And come back in your room, slightly more happier, and you work on the problem. Well, that's basically how I have dealt with a lot of this. And secondary, in a very, very more practical sense, again, especially in astrophysics, might not be so much in other parts of physics or other parts of science, it is extremely collaborative.
Like your own research is a part of a lot of people coming together.
Yes, exactly. So my research group has has 40 people. Though my project, so my group in PT has 40 different. And I know I can rely on them. Not all of them are good friends of mine, but they are excellent colleagues. And I know I can ask them questions. I know I can email them at 3 a.m. in the morning, and in a couple of days I will get a reply. They will kind of help me through the whole problem. So not just my collaboration though. Astronomy in general is a science without boundaries to the fullest, more than any other field. The telescopes which we use are often in different countries. The collaborations which we have are often across continents. Because the best telescopes in the world, the GMRT here, which is a very good low frequency telescope, is used by so many people from all across the world. And people don't stop and think, bhai, ye India ka telescope hai, main use nahi karega. People use it because it's a cool telescope, it's a useful telescope. The same thing what Indian scientists do when they use the Hubble Space Telescope. It is launched by NASA and ESA, but if you have a creative project to do with Hubble, the Hubble people will let you use Hubble for your own science. And people who won't take nationalities, which they still have a part, of course, they still play a role. We live in a society, haha. They play a role there, but the collaborativeness of astronomy also makes you feel that you are a part of a global community trying to tackle problems. Not just people from the past, as I said before, but people alive today who are using these tools, using these telescopes, using these scientific techniques to meet their own goals. So that also helps, that general communication and this collaborative effort, specifically in astronomy. Again, personal observation and observation of a couple of other better scientists than I am currently, who have observed, is that on average, people in astronomy are generally more humble and friendly. On average, they and that ends up being a very nice thing when you are in trouble of any kind. It could be personal trouble, it could be scientific trouble, it could be a cultural problem you might be facing. If you reach out in the astronomical community, more than likely there will be someone who will stand with you, and kind of help you out through the whole issue. So, reaching out to your own friends and reaching out to the astronomical community is always something which you can do and which you should do if you are in this particular field, because you will find people who will help you out. That's a lovely part. It is something. apart from what astronomy and astrophysics gives the world, which is the knowledge of the sky, the stars, of celestial objects, astronomy and astrophysics is also a social experiment in which people cross cultures can come together to solve huge, massive problems together. It is like a beacon of hope of what humanity can do together if they, set an eyes to solve a particular problem. And we are going to need that kind of collaboration because we are facing issues like, climate change in the future. We are going to need these global models of collaboration, of people getting together and solving and fixing problems together. So, it's kind of a beacon of hope, the whole thing. And on a very personal level, apart from these grand ideas, which I'm, vomiting from my mouth, I got enormous support from my own friend and my classmates, who, being a part of this really friendly astronomical community, are like amazing people in their own right, who got on Discord calls at like 3 a.m. in the morning every single night and chatted and supported each other and cried together and laughed together and made sure that the problems are solved and, got things done. Eventually, everyone in our class, some people are early, some people are late, everyone was able to finish their thesis and everyone, did fairly well. It is obviously a spectrum. Some people were able to do better because they got better guides. Some people not so much because there are personal issues and issues with guides, so on and so forth. But we pushed each other through the entire process and we are crossed that border now. Our master's degree is finished. And here we are with all these lessons which we have learned before.
I think that's a really good point to wrap the podcast.
Sure.
Thank you so much, man.
Yeah.
That was really awesome.
Hope you loved the episode. Subscribe to our show and see you next Saturday.